All right, so we're going to get into chapter 7 here. And of course, 7.1 is the first section. And this chapter is about what are called differential equations. And so this section here is just a quick intro. And it is rather short, but it'll sort of give us the foundation of what we'll be doing. If you can see parenthetically below the phrase differential equations, you can see I wrote diff EQs. That's the typical short speak, if you will, for expressing that you're working with differential equations. Look at this diff EQ. So you'll hear me say that. And I always tell students, if you ever are around someone who took maths or science or engineering classes when they were in college, and you can work in the phrase diff EQ, then you'll see somebody's ears perk up and they'll think you know something. And it's a good way of kind of showing off a little bit of your knowledge if you could work the phrase diff EQ into the conversation. And generally, you won't have to worry about understanding diff EQs at a very deep level, because they probably won't remember them very well either, and they'll just have some sort of kindred experience saying, oh, I know what those are, and you know what those are, so we're both pretty smart. Anyway, enough of that digression. In general, diff EQs are a vast subject, and you can take whole classes in college based on just some small subset of a class of differential equations. You can take classes on what are called partial differential equations or ordinary differential equations. There's just those ODEs and PDEs, and they're a vast subject, and still on the forefront of a lot of research that happens in applied mathematics. You'll see a lot of work with differential equations, and so it's broad. And what we cover here is a very small drop in a very large ocean of the subject. So, but we got to get you some foundation, because for the AP, you have to know some basics. So what is a differential equation? We've actually worked with them a little bit already, but we just didn't call them that much, except for some homework examples where the concept was introduced. But a differential equation it's an equation that contains an unknown function and or one or more of its derivatives. Okay, well, it's an equation because it's in the name, differential equation, and the differential part is referring to derivatives. Okay, so it's an equation that has derivatives in it. It could be a first derivative, a second derivative, or some higher order derivative like that. It could be multiple. It could have a first derivative and a second derivative, and the function itself, or other combinations of those, with factors and multipliers, constants, and all kinds of other stuff. Like I said, we deal with a very small subset of the whole field, and so we're going to just do some basic stuff. Let's take a look at a simple example. I say it's simple in the sense that as I wrote here, it's something you should be familiar with, although writing it like this is probably not very familiar, but it is a function that you're familiar with. This is a differential equation. It's a very powerful one, very common one that we see and use quite a bit, and one that you should learn to recognize. So let's talk about it a little bit, and then I'll tell you why it should be familiar to you, or I'll demonstrate how you should have some familiarity with it. First of all, let's look at the parts here. Well, at least it matches the definition that I gave you, this loose definition that I wrote above. It's an equation, and it has a function in it. The function is y. Okay, and it has the derivative of the function in there as well. So we have a couple different things in here that meets the definition. Now, it doesn't have a higher order derivative. It doesn't have a second or a third or a fourth derivative or anything like that in it. And it does have the function y. Not all differential equations actually have the function itself in it, but they could, and this one does. Okay, so it meets the definition. Now, let's talk a little bit more about what it actually is telling us here. We're saying that the rate of change of y, that's what the left-hand side says, dy over dx is the rate of change of y with respect to x. We're saying that the rate of change of y with respect to x is k times y, or in another more common way of saying this, proportional to y. Maybe you recall from back in pre-cal, there was a section where you learned about some phrases that we use in math and physics and science and whatnot, where the directly proportional to phrase or inversely proportional to phrase. This comes from that same language. The rate of change of y with respect to x is directly proportional to y, or some constant k times y. And again, this is something that you should be familiar with. I would challenge you for a moment to think, can you conjure up in your mind a common function that we've used quite a bit, whose derivative is proportional to itself, meaning its derivative is a constant times itself? Again, I would encourage you to pause the video for a moment and think that through. And hopefully you're able to come up with that function. Let's take a look at an example here. So let's let y equal a to the power of x. Well, if I take the derivative of y with respect to x, what do I get? Well, I get a to the power of x times the natural log of the base times the natural log of y. I'm sorry, the natural log of a. So what is that? Well, if we're paying close enough attention here, dy over dx, well, a to the x is just y, so this is the natural log of a times a to the x, but a to the x is just y, so this is just the dy over dx is just k times y, where k is equal to the natural log of x. Sorry, the natural log of a, natural log of a. And so we do have the exact same pattern that we had up here, okay? The rate of change of the function is proportional to itself, is a constant times itself. That constant in this case is the natural log of the base. So the function that I was hoping you would find is the exponential function, or is an exponential function. Right now, as I'm recording this, we're in the middle of our dismissal from school due to the coronavirus or COVID-19 pandemic that's happening. And so perhaps in all this stuff that's going on in the news, you've been paying attention to a little bit of some of the graphs that have been coming out, and you can see there's been a lot of talk about exponential growth for this. Even I've been sending out tweets on Twitter showing graphs that have some exponential growth to it. I have a little bit of a pet peeve when you hear people on the news or in media say something is growing exponentially. Oftentimes it's not. And I don't trust somebody who says that phrase unless they are a scientist, mathematician, or something of the sort who have some experience with true exponential growth. This definition, what's in this box, this is what it means for something to grow exponentially. It means it's growing at a rate proportional to itself, okay? That's the definition of exponential growth. And there are a lot of people who use the phrase something is growing exponentially euphemistically, where they're just trying to illustrate something's growing really, really rapidly. But that growth might be polynomial, it doesn't have to be exponential. And so, or something else to them, it might even be linear and they're just not paying close enough attention, might just have a steep slope. So that's one thing that you can pay attention to. Maybe not so much these days. You can see a lot of scientists saying things have been exponential for a while. They're going to level off eventually. It can't be exponential in perpetuity. It's got to come to a point where the curve is going to flatten. And there's another type of curve that we learned in the BC class called the logistic differential equation, which models growth of populations and whatnot in under more realistic conditions, where you have limitations of food supply and limitations of space and other considerations, which would have exponential growth at the beginning of the growth cycle, or approximate exponential growth, that eventually turns to a concave down curve, where the graph is no longer increasing at a rate proportional to itself. But that's a topic for the future. The point is, let's go back to this for a moment. We're starting to study these things called differential equations, okay? And I gave you one. That's what's written in red here in this box. It's an equation. It's got a function in it. It's got its derivative in it. And what we have to be able to do is some basic on some basic levels, we have to be able to, come up with one of three things, or maybe more than one of these things, but there's three things that we're trying to do. We're trying to solve in some way a differential equation. And there's three ways of doing that solving. That's the three things I was referring to. We may be looking for a function that is the solution for it if we can find it. That's ideal. We'd love to find the function. In this example here, the solution to this differential equation is y equals a to the power of x. That's great. We'd really want to know that. We'd put it in a more general way. I should say this is a solution to that differential equation. No, you got me. I got myself thinking about that. But anyways, I'm not going to get bogged up in specifics at the moment. So we're either looking for a function that solves the differential equation, or I'm looking for a way of approximating the solution to the differential equation. So whenever we're giving a differential equation, we're trying to do something. We're trying to solve it if we can analytically for a solution, or we're trying to approximate a solution as best we can, which is one of the things that we often do in calculus when we can't find an exact answer. We find an approximation. So those are the goals of working with the differential equation. Let me step back one more step for just a moment. Why are we even learning this topic? Well, differential equations are a way of modeling things that happen in the world around us. Remember, the study of calculus is about change. We're trying to figure out how fast things are changing. That's the idea of the rate of change concept. And how things are accumulating based on knowing how fast things are changing. That's the integral concept. Okay, the integral is the accumulator, that area bounded by a curve, or that net signed area, that net change in concept. Okay, and so calculus is all about change, and a differential equation is an equation that has within it a model for something that's changing. Okay, the dy over dx equals k times y is a model for something called exponential growth. And so if something is growing exponentially, it would have a differential equation that would look like this. Okay, or maybe some slight variation on there. But with that said, the point is that the differential equation is used to model something that's happening in the world. It's kind of like a mathematician's or a scientist's crystal ball to try to figure out and make a prediction about the future. If I know how something is changing in some relationship, in some equation, some diffeq, then I can hopefully solve that diffeq for a function that will give me a way of predicting what's going to happen in the future, or get an approximate solution for what's going to happen in the future. And that's what's happening a lot right now with this pandemic that's going on. Their models, not all of them are based off of just simple diffeqs. There are other types of models that people build. But nonetheless, with that model, what they're trying to do is make a prediction about the future. Models are usually wrong, but they give us an indication of behavior and what's happening in the future. So it's a crystal ball, but it's a very foggy crystal ball that doesn't give us an exact understanding of the future, because the future has too many variables. But it does give us hopefully a little clearer picture than if we didn't have the model to use at all. So as I mentioned a moment ago, there are three ways to solve, quote unquote, a differential equation. Three techniques, three ways that we're going to be having to have some experience with. Actually, in the AB class, we only really primarily work with two of these ways, and the third way comes into the BC class. So, well, the first thing we're doing is, in the ideal way, are the analytical techniques. The analytical techniques are the ideal way of solving it. If we can solve a differential equation analytically, that means we're coming up with a precise solution to the diffeq. Okay, and if we have a precise solution, then our answers are not approximations. Although all models are giving us approximate answers, these approximate answers are the most accurate approximate answers, but they're exact solutions. The failure is not in the solution. The failure is in that we're just doing a model and we're not accounting for every possible variable that could come into play. The analytical techniques, we've actually done this a little bit. Anytime we found or we're finding an antiderivative, we were actually solving a differential equation, a really basic, one might call trivial differential equation, but we're still solving a differential equation. So anytime you're taking an antiderivative, so antiderivatives are solving or one of our analytical techniques for solving diffie-qs. The other technique that we're going to need is what's called, I'm writing down the wrong thing here, it's called separation of variables. This is something that we're going to learn in section 7.3, and it's the only analytical technique that we learned in the AB class. In fact, in all of first-year calculus for solving this. If you want more advanced techniques beyond this, then you got to go into a higher level class in college. Okay, so those are our analytical techniques. Now we have the next type are qualitative. Oops. Now, qualitative techniques allow us to look. This is when we can't find an analytical solution, generally speaking. We look at the qualities that the differential equation would predict about the behavior of the function. Okay, what qualities are we talking about? Well, the qualities that we've studied. Is the graph going to be increasing or decreasing on a certain interval based on what the differential equation is telling us? Is the graph going to be concave up or concave down? Again, based on what the differential equation is telling us. Is it going to exist or not exist? Based on, again, what the diffie-q tells us, okay? So this is using graphs, okay? If you remember way back when, we actually would look at the graph of a derivative, and from the graph of the derivative, we would sketch the graph of an antiderivative of that function. That's what we're talking about here, okay? That similar type of thing, looking at the derivative and seeing what the qualities of the derivative tell us about the qualities of the function itself, okay? The other thing we're going to do is we're going to be looking at slope fields, and that's in section 7.2. And slope fields are a way of sort of quantifying what the derivative is telling us at a certain point or at a collection of points that can then tell us about the behavior of the solution to that diffie-q. Okay, should the solution curve be increasing concave up or increasing concave down, and those sorts of things. Does it level off? Does it have an asymptote somewhere? Again, this is stuff that we would see from the qualities of the differential equation are based on the qualities of the differential equation to determine qualities of the function itself. And the third type are the quantitative techniques. Now, the quantitative techniques are techniques that allow us to use some basic information along with the diffie-q, some like initial value, and then to start to construct approximate values for the solution curve at a certain point. I can't solve it analytically. I can't, or I could possibly look at the qualities of it, but I want to know something a little bit more precise. I want to get an output, an approximation to the output of the function. So then I start looking at the quantitative ways of doing this. Now, there are many quantitative ways. We at the AB level don't learn any of them, and at the BC level we learn one. It's called Euler's method. And so those of you who go on to the next class, we will learn that technique there. It's not an overly challenging technique, and it kind of piggies back on our linear approximations that we did in an earlier couple sections. But it's a way of taking those types of things, the linear approximation technique, and making it better to get some better approximations. All right, let's take a look at a simple example. And this is an example that is phrased from section 7.1 or chapter 7 in general, but it doesn't require anything new that we've been learning from chapter 7, except from maybe just the understanding that what we're doing is solving a diffie-q. So solve the differential equation for the particular solution y equals f of x. We're given that y prime is equal to 2 sine x minus 6x squared plus e to the x, and that y of 0 is equal to 5. So a couple things. I'm trying to phrase this in a similar way that the AP exam would phrase it. And one way we can see this is, they say solve for the particular solution, y equals f of x. That's a common phrasing that they use, and what they're saying is you've got to solve for y. Okay, in this example here, it's going to be rather simple to solve for y. Y is going to come out in the answer just naturally. So when you see y equals f of x here, make sure you solve for y. It's not always the case that we're going to be able to solve for y. The other thing, it says the particular solution. That's the other part of that phrase that's important. When you see particular solution, they're doing that because they gave you a value, an output at a particular input, a point that the graph has to go through. Remember, when we're using an antiderivative to solve an equation, we end up with what we've called before is a family of curves. And so the family of curves all have this plus c. They're all differ by that constant, that vertical shift from the plus c. And this y of 0 equals 5 is going to allow us to select a certain member of the family, and then that particular member is the one we're looking for. Okay, so again, this is a rather straightforward problem. So this isn't something that we haven't been able to do before. In order to find y, we're going to need to take an antiderivative here. So if we want to put some notation to this, we could do something like this. We can put the integral of y prime with respect to x, and that's going to be the integral of all of this stuff over here, also with respect to x. I don't always actually write this step down. Sometimes we just go into finding the antiderivative. Over here, we're going to get y. I'll comment why I'm not putting y plus c on this side in just a moment. But an antiderivative of 2 sine x is going to be negative 2 cosine of x. And then we're going to get minus, and then it's going to be 2x cubed plus e to the x, and then plus a constant. Okay. Now, again, I said I'll comment. I don't put y plus c over here, because if I did, then I would have to put, I'm just going to put a box here for all the stuff that comes before the plus c. I'd have to put a separate plus c sub 2 over here like this to note that those two things aren't the same constants. But mathematically, I mean, what's the big deal? I could just subtract c1 from both sides, or c2, it doesn't really matter. Subtract c1 from both sides, and I would get y is equal to all of this negative 2 cosine of x minus 2x cubed plus e to the x plus, well, c2 minus c1, that's just some other constant. I'm just going to call that c. And so all I need back up here in the original case is all I need is one constant to account for all the constants that would occur in taking an antiderivative. I don't need a constant for each individual term. I don't need a constant on this side. I just need one constant that'll take care of every single constant that's there. All right, so we have our family of curves. That's this equation right here. But what we want is the particular member that hits the point 0, 5. And so I got to do a little bit more work. So I'm going to plug in, I'll note so that my reader knows what I'm doing. At the point 0, 5, I'm going to plug in 5 for y and 0 for x. And so I don't really need to write this all down in this much detail, but I am for the first example. So let's solve for c. Cosine of 0 is 1, so that's negative 2. That middle term is 0, and e to the 0 is 1. So this simplifies to this. So negative 2 and 1, of course, is negative 1. So c is going to be equal to 6. And so then our solution to this diffie q our particular solution is negative 2, y equals negative 2 cosine of x minus 2x cubed plus e to the x plus 6. And that's our answer. All right, let's switch to a different example here. So what I'm going to do, or what I'm doing here, is I'm giving you a differential equation, a much more complicated differential equation than the ones that you've seen so far, okay? Let's first note that something's different about this one than both of the previous examples that I gave you. First example I gave you is dy over dx is equal to k times y. So I had the differential equation, or the derivative dy over dx on one side, and just y on the other. I know there's a k. K is a constant. Constants we don't care that much about. We account for them, but we don't concern ourselves. There was no x. It was just k times y. Okay. In our second example, the one we just worked out, it was y prime, which is the same as dy over dx, is equal to, in the entire, all the terms on the entire right side were all in terms of x. There wasn't a mixture of x's and y's. It was just all x on that side. So the first example, dy over dx is equal to something in terms of y. The second example, dy over dx is something in terms of x. Now we have a mixture here. We have dy over dt. So y is our dependent variable and t is our independent variable. That's our derivative over here. And on the right-hand side, I have t squared, and then this much more ugly expression involving y. But I have both t and y on both sides here, and that's important. That's important to understand. Whoops, I'm trying to. Sorry, now I'm playing with this different screen that I'm used to I'm not used to working with at the moment. All right, so anyway, so it's a little bit different. Okay, this is how differential equations are. They have these qualities where, or these examples where they could be much more complicated. Okay, my question is, can this graph that you're seeing right here, okay, be a solution to this differential equation? I'm pausing for a moment, letting that sink in. Can this graph be a solution to this differential equation? If I were able to solve this, does this graph have all the right properties and qualities and features that we would expect from the solution to this differential equation? Now, I know we're barely scratching the surface into this topic here, and you are probably really, really confused, but that's okay. This is part of the learning process. Okay, what you need to sit there and wrestle with is, are the features of this graph consistent with what y would equal? Okay, so can this be a graph of y? That's what I'm asking, because the solution to this would be the function y. Okay, because I got y here, it's dy over dt. So can this be a function of y? That's the question. I'd love for you to pause and stare at the graph a little bit and think about what's going on. Okay, now I'm going to get into this. Hopefully you had a chance to think about it. Right or wrong, it doesn't matter. Thinking about it is more important than just coming up with a right answer. It's did you put your brain to work in this case? Excuse my dog barking in the background if she does. All right, well, let's take a look here. Okay. All right, sorry, I had to pause. All right, let's look at this graph a little bit. Notice that over here, the graph is decreasing. And over here, the graph is decreasing. Now, why do I care about that? Well, if I look up here at the differential equation, there's a bit of a contradiction here. Remember, the derivative tells us things about the graph. The derivative tells us the slope of the tangent line, but it also tells us when the graph is increasing or decreasing. So on this region right over here, if the graph is decreasing, this is the graph of y, in this section here, y is decreasing, that means the derivative of y on this interval would have to be negative. All right, well, let's see here. Well, this 1, 2, 3, those are t values. So let's just look at this point here. T equals 1. Okay, so I have to put 1 in for t. The y value, oh, let's just say that's a half. Okay, so this is going to be a half minus a half to the third power. And then I got to raise all of that to the fourth power. I'm not even going to do the calculation of the half minus a half cubed. I'm going to get 1 squared, which is 1 times something to the fourth power. That's going to be positive. Positive. This is going to be greater than 0. This is always going to be greater than 0 because of this, square that I have here. Choose a negative value of t. I'm going to square it if I plug it into this diffeq. And then whatever value I plug in for y, I'm going to end up raising this difference after I do that inner calculation to the fourth power. So that each of those are both going to be positive. And a positive times a positive is always going to be greater than 0. So a solution to this differential equation should never be decreasing. And this graph is decreasing on 2 different intervals. So can this graph be a solution to the differential equation? Absolutely not. Hopefully you figured that out on your own. So hopefully now you got the hang of it a little bit, and I'm going to ask you to take a look at the same differential equation, but now we're going to look at a different graph. And go ahead and pause the video and see if you think this graph could be y. Could this be a solution to the differential equation that you see? All right, so hopefully you came up with an answer. Now, if we look at it, we said before with this differential equation, because of these exponents up here, that we should always see that the solution can never be decreasing, and this solution never is decreasing. So, yeah, maybe this is a solution to the differential equation. But we have to be careful here. There's some other things that might throw us off a little bit. For instance, how about this point right here when t is equal to 0, this y-intercept is 0, 4. Well, if I take that point, does the graph have the right qualities at that point as the diffeq suggests it should? Well, at that point, the t value is 0, and 0 squared is 0. The y value is 4, so 4 minus 4 cubed to the fourth power. None of that matters. I don't care what that is, because I'm still going to multiply it by 0. That has to equal 0. And if the derivative at some point equals 0, what does that tell us about the graph? Well, the graph would have to have a horizontal tangent line at that point. And clearly, I hope it's clear, this tangent line here is not horizontal. Tangent block as I put on there, but the tangent line is not horizontal. So clearly that this graph cannot be the solution to this differential equation. All right, let's try this one more time. I'm sorry, I should have adjusted that before we got to this point. So pause the video and go see if you think this graph could be y. Could this be a solution to the differential equation? Just to make sure, if some of you are still not quite understanding what I'm saying, I'm not asking if this graph here is the graph of the derivative. I'm asking is the derivative of this graph given by this equation right here, okay? So is this the antiderivative of this expression that we have up here? If you want to use some loose terms here, we wouldn't necessarily call it an antiderivative in one sense, but is this a solution curve analogous to an antiderivative? Well, hopefully you just came back from pausing the video and you have an answer. So similar to the last one, the last two, this graph can never be decreasing. Okay, it's not. And so at least we don't have a violation like the first example. And the second example, we looked at the y-intercept and we saw that at the y-intercept, we should have a horizontal tangent line. And this graph does, okay? If I plug in 0 for t, I get 0. I plug in 1 for y, I get another 0. And 0 times 0, of course, is 0. And so we do get a horizontal tangent line. So Maybe this is a solution to the differential equation. Well, we got to be careful. We got to make sure we look in enough places and make sure that we have enough data to support this. One data point is not proof. Okay, one data point can disprove something, but one data point cannot prove something. Okay, so let's go look someplace else. Let's go see if we can find something to disprove this. What about this point right here at this -1, 0? Well, t-value is -1, so I'd have to put -1 over here and square it, but whoa, the y value is 0, which means all of this is going to be 0, and if all that is 0, that means we should have a horizontal tangent line at this point also, and clearly we don't have a horizontal tangent line at that point. And so this too is not a solution to the differential equation. All right, so our work in these three examples here were just to try to illustrate ways of seeing, okay? We want to be able to see the correct qualities in a solution curve, and we can take a look and analyze this diffie-q and figure out where we would expect, and in this example, the graph's always going to be increase or never going to be decreasing. It's not increasing where the tangent line is horizontal at that particular point, but nonetheless, never decreasing. And that's a quality that we need to see. And although this graph has it, it's still missing other features that we would need to see. But we're starting to understand and hopefully train our eye and tray our way of thinking about visualizing diffie-qs. All right, here's another example. I'm calling this 2. I know we did those graphs, and you might think those were like 2, A, B, and C. And if that's what you did, call this 3. It doesn't matter. Consider the diffie-q y double prime plus 2y prime plus y equals 0. And we'll have multiple parts for this one. Part A, is y equals e to the power of t a solution to this diffie-q? So we're asking a similar question as to the last one, where I give you a differential equation. The last thing was I'd give you a graph and ask you, is that a solution? Now I'm giving you the function and asking you, is this a solution? So we're just, instead of doing this graphically, we're doing this analytically. So how am I going to tell if this is a differential equation? Well, analogously, if you go back to like, I don't know, 4th grade or something, there was a time. I'm gonna bring you back and do this by analogy here. There was a time way back when where you would be given the equation of a line, like y equals 2x plus 3 or something like that, and they would ask you, is let's see, 5 comma 12 on the line or on the graph of this line, on the graph of that thing right there. And if you remember back when you would do this in preschool or whenever it was, you would take the coordinates of the point and you'd plug them in for x and y and see if you got a true statement or not. So you plug in 12 and then you'd get on this side, and we would want to see if that's equal to 2 times 5 plus 3. Well, this side's 13, so 12 is not the same as 13. So the answer to the question was no, because we ended up with a false statement. 12 equals 13 is a false statement. Well, that's what we're essentially doing here, is we're now trying to plug in, if you will, the values we would get from y equals e to the t for y double prime and y prime and y, and then see if we get a true statement or not. Okay, so let's see. Let's go back and let's calculate. Okay, so if y is equal to e to the power of t, then what's y prime? Well, y prime would also be e to the t, because it's just e to the t. Excuse me. And then what's y double prime? That's also e to the t. Now I want to take those values and plug them into the equation on the left-hand side there and see if they come out to be 0. So y double prime is e to the t plus 2 times y prime, or 2 times e to the t, plus e to the t, because that's just what y is equal to. And what does that equal? That's 1, 2, 3, 4 times e to the t. Well, is that always 0? No, it's never 0. So therefore, this is not a solution y equals e to the t is not a solution to this differential equation, because I'd have to get a true statement out of that, and I didn't. All right, so now part B, is y equals e to the negative t a solution? And I rewrote the diffie down here for my own benefit, maybe yours as well. Pause the video and go try to work it out for yourself. All right, so hopefully you find out what's going on here. Y prime is going to be negative e to the negative t. Y double prime is going to be just e to the negative t. And so let's go plug those things in. So y double prime e to the negative t plus 2 times negative e to the negative t. That's what y prime is. And then plus y, which is e to the negative t. And, well, look at this. We got, whoops, I put negative 2 over here. Excuse me, that's negative t. But we got e to the negative t and e to the negative t, which together make 2 e to the negative t. And then this is negative 2e to the negative t. And if I combine all that, I get 0, which is what we want. So yes, yes, y equals e to the negative t is a solution to that diffie. Now, lazily here, I didn't write the question out again, but now, same question. Is y equals t times e to the negative t a solution to this diffie? Let's go work that out. See if you get a yes or no answer to that. All right, so we're going to take some derivatives here. So if I make sure to apply the product rule, I get 1, derivative t with respect to t is 1, times the second factor, e to the negative t, plus the derivative of e to the negative t, which is negative e to the negative t, times the first factor t. Let's see. So I'm going to write that as e to the negative t minus t times e to the negative t. And then I'm going to take the derivative again. So y double prime. I'm going to be a little clever. The derivative of e to the negative t, well, that's what we were just finding. That's all of this here. So all of this is the derivative of that first part, so that I'm going to end up with just e to the negative t minus t times e to the negative t. And then I got to take the derivative. No, that's wrong. That's the second part. I'm sorry. I'm not paying close enough attention. Misspoke. Let me fix that. That's all of this stuff here is all the stuff I'm subtracting here. Sorry. So all of that goes in parentheses here. That's the derivative of the second part, the t e to the negative t, and then I got to subtract that. Okay, and then the derivative of e to the negative t, the first part is just negative e to the negative t. Excuse that little mistake. All right, so after working through that little bit of a mistake, so I distribute this negative and combine, I get negative 2e to the negative t plus t e to the negative t. And I got to plug both of those things into that diffie and see in the right spots and see what happens. So y double prime, negative 2e to the negative t plus t e to the negative t plus 2 times y prime, which is e to the negative t minus t e to the negative t. I don't know why I keep doing that on that one. And then plus y, which is just t times e to the negative t. And we've got a little bit of arithmetic to do. And so I can combine this one here and this one here to get 2t e to the negative t, and then distribute this 2, and I get plus 2 e to the negative t minus 2t e to the negative t. And it looks like this and this cancel, and this cancel, and all of this equals 0. And we have found another solution, or we have another solution to that differential equation. So again, the answer is yes. All right, that's where I'm going to end the video. You'll get some more practice with the Desmos activity to get you to do some of these things, and we'll then pretty soon get into sections 7.2 and 7.3. Go study.